Hello, everyone. Welcome to our live session for today, Thursday, October 19th. My name is Matthew. I'm one of the course staff and instructors for our online classes, but if you've joined us from some other source, welcome. We are excited to be here today answering all of your questions about astronomy, astrobiology, history and philosophy of science. Chris, why don't you introduce yourself and then we will start taking questions.
Right, welcome everyone. Whether you're in one of our MOOCs or just found this by some other means, we're happy to have you and for me to try and answer any question on astronomy.
Excellent. For those of you who are new or have not asked a question before, post your questions in the chat. I will grab them from there. Please ask your questions only once. We do see them. We just tend to jump around a lot so that everybody can get a choice or a chance to ask a question, and we get a variety of questions. Make sure you like and subscribe to our channel so you hear about upcoming live sessions. We also have a Google group, like a listserv, like an email listserv. Posted that at the beginning of the chat. So if you'd like to join that, we will send out emails through that if you're not receiving emails through our online classes. The first question is from one of our live participants. Pecornin would like to know, hello, Professor. When light gets redshifted, does ultraviolet light become visible light?
Yes, all the redshift effect applies across all wavelengths. So redshift in astronomy terms is different from the Doppler shift. It's actually a cosmological redshift, which means it's caused by the expansion of space-time. And that basically just means that the metric of space, the way that space is measured, the distances in the vacuum of space, increases over time. And that means any waves traveling through that space, such as from electromagnetic radiation, those waves also are stretched by the expanding space. And that applies to whatever the wavelength is. So infrared waves get stretched to form microwaves, visible light gets stretched to form infrared waves, and ultraviolet light gets stretched into the visible part of the spectrum. So it applies across the entire electromagnetic spectrum.
Excellent. The next question is from an email from Wendy Traver. Is it likely the planets in our solar system will become rogue after the death of our sun?
So the fate of our solar system is an interesting question because it's actually quite hard to model. The planets in our solar system are long-term stable, which means if you play the orbits forward for tens or hundreds of millions of years, they tend to stay the way they are. But on longer time scales than that, and where computer simulations are required and they're not even perfect, it's possible that interactions among the planets will cause one or more of them to be ejected. Now, what happens when the sun dies? Well, when the sun dies, there's primarily the loss of light from the fusion energy source, but also there's a red giant phase. The red giant envelope will extend almost to the orbit of Mars. It's a little hard to tell exactly how far. So it will encompass the inner planets, and it will move them slightly in their orbits. So certainly the death of the sun leads to the possibility that the inner solar system will be destabilized because the sun's expanding envelope will exert a push on those planets as it travels outwards. So yes, there's certainly a possibility that the inner solar system will become unstable, leading to the ejection of one or more of the terrestrial planets in 4 billion years or so.
The next question is from Faisal. Can we say that there is new chemistry or new physics in the universe other than the physics or chemistry of experiments on Earth? And to what extent is this idea accepted in scientific circles?
So the universality of the laws of nature is a major question, and it's a one for experimental study, but it's also hard to measure the laws of nature far away from the Earth. The universality of physics is fairly reliably understood because we see how objects move in the distant universe, and we see gravity operating more or less the same way that it does in the nearby universe. The gravity, of course, is driven by dark matter as well as visible matter, and we have that in the local universe as well as the distant universe. So certainly the law of gravity appears to be universal. And the electromagnetic law that leads to electromagnetic radiation is also universal, because light and other forms of radiation are seen throughout the universe. So generalizing, it does seem like the laws of physics are universal. Chemistry also seems to be universal. We have never seen a spectral signature of an element that's not in the periodic table in studying distant objects, whether they're exoplanets or distant galaxies. So it's likely that the periodic table that we measure from terrestrial materials is a universal periodic table. Those are all the elements there are, the stable ones and the unstable ones beyond uranium. So universal chemistry and universal physics is a premise. It is testable at some level, but not completely.
The next question is from one of our, it's actually a follow-up on the previous rogue planet question. The question is, would rogue planets have a longer lifespan than bound planets?
Well, it depends what we mean by lifespan of a rogue planet. A rogue planet is a planet ejected from its solar system, so we'll just use that definition. The planet itself is a rocky object, and so it's going to be pretty invulnerable to its situation, and it will last equally long whether it's orbiting a star or floating through interstellar space. Now, if we're talking about a living rogue planet, that is a rogue planet with an atmosphere and potentially biology on it, then the longevity of that is less clear, because obviously a planet orbiting a star has the solar or stellar radiation to support that life, whereas a rogue planet in deep space has only got the energy source of internal geology, which, even if with a super Earth, will not be very large. So rogue planets are unlikely to be living planets unless, in certain cases, super Earths might be biologically viable. But the planet themselves will endure for billions or maybe even trillions of years.
The next question, supernova in 1993J was a class K star and a type 2 supernova, which means the supernova wasn't fueled by another star. How can a K star, which is lower temperature than our sun, go supernova all by itself?
It's not easy for a star that's isolated and below the Chandrasekhar limit to become a supernova. So it does need to gain material from outside. It doesn't have to necessarily be in a binary system for that to happen. Stars can be in dense regions of the Milky Way where there's a lot of interstellar material, and so stars can accrete material by gravity, and that can possibly trigger them over the edge of the Chandrasekhar limit and into a supernova. So we'd have to know a lot more about the environment of that star to understand whether it somehow accreted interstellar material and therefore went supernova that way.
The next question is related to our last live session, where we were talking about the overview effect. Prasanta asks, how might the experience of the overview effect influence the mindset of astronauts, leading to a greater commitment to addressing global challenges upon returning to Earth?
I think astronauts are often profoundly affected by the experience of being in orbit. Remember, the number of astronauts is modest. I think it's still less than 700. Most of those, of course, from the major space programs of the United States, Russia, and China, but now with a growing number of civilians from commercial launches. And they've all expressed the profound nature of the experience of being in orbit. And astronauts, when they come down, and also especially when they retire from their space agency like NASA, they are very committed to outreach and to public speaking. They're not all equally good at it, of course, but they mostly do it, and some of them are very good at it. So I think astronauts who've had that experience, very many of them, a good fraction of them, are out there on the road visiting places, going to schools, giving public lectures, and explaining why the Earth is a very precious place and how it appears from space and how it makes our divisions sort of fade into insignificance because it's just one world. So I think that group of people, the ones who've seen the Earth from above, are extremely valuable proponents of caretaking the planet.
The next question is from Kivan Sharma, who's on with us live. Hi, Professor. Why does the universe become increasingly symmetrical at large scales, but asymmetrical at small scales? Do you think we have not achieved scales small enough where symmetry exists again?
So it depends on what we mean by symmetry here. If we mean isotropy or uniformity, then the uniformity doesn't exist on small scales because of gravity and because of the other forces of nature. So the electromagnetic force also creates some asymmetry on smaller scales. On the largest scales, we have the cosmological principle, which is that the largest regions of the universe are indistinguishable from each other on average because their average properties of density, temperature, and so on are the same. And so the symmetry of large scales is a function of the cosmological principle and the fact that the universe is isotropic and uniform on the largest scales.
The next question is from an email. Mario Flores would like to know, is the universe actually infinite?
It's not clear if the universe is infinite. It's certainly possible and accommodated by our standard theory, the Big Bang theory of the formation of the universe. So the Big Bang has an expanding space-time starting from a singularity event 13.7 billion years ago, and it is possible that there's no edge to this expansion. This expansion just continues without limit. And certainly we have no observational sign of an edge to space. If we look out in space, we are essentially using the telescopes as time machines to look back in time. And so just by observationally going out in space, eventually we just come back to the time before there were any galaxies. And so we run out of things with which we can measure the universe. So there is no evidence that the universe isn't infinite, and it's certainly allowed by the theory.
Excellent. The next question is from Irina, who's on with us live. How do we investigate dark matter, and are there new ways for that or other ideas for how to investigate it?
There are basically two ways to investigate dark matter. One way is astronomically, and it's the astronomy measurements of dark matter that led to the idea that there is dark matter in the universe, and that's using the motions of objects and the law of gravity to infer the mass and find on all scales, from galaxies to even larger scales, clusters and superclusters, and the universe as a whole, that there's a lot more mass driving the gravity than in visible material. And that's the evidence for dark matter. And it's been done many ways and on many different scales. The other way to understand dark matter is physically, and that would require a physics-type experiment. And so there are a set of experiments underway in labs and sometimes in deep mines to shield from cosmic rays, create a quiet environment, where solid-state detectors or gaseous detectors are being used to try and look for the dark matter particle. And we assume it's a fundamental particle at this level. Since the particle does not interact with light or radiation, that's why it's dark matter, these particles are detected by their kinematic properties. Essentially, you're looking for the dark matter particle to collide with atoms or molecules in the detector and for that energy to be registered somehow. So those are experiments that are underway. They haven't succeeded yet, but it's certainly a very direct way to interrogate dark matter and perhaps find out what it is.
The next question is from Lawrence K., who's on with us live. Hi, Professor. When distant light is redshifted, where do the photons' energy, or where does the photons' energy go? Is energy conservation local? Doesn't the mass energy density of the universe always stay the same?
That's a good question. So how does the redshift or expanding universe square with the law of conservation of energy? So when the universe is expanding, the energy of each photon is going down because it's being redshifted, and it's filling a larger space. So the energy density of that space is declining. As the universe expands, the density of matter goes down as the radius or the size cubed, because that's just volume. However, the energy density of radiation goes down as the fourth power of the size or radius, because Their photons are distributed in a larger volume, but each of the photons is being redshifted by another factor equal to 1 plus the redshift. So the redshift causes the energy density of radiation to go down faster than the energy density of matter. So when you do the conservation of mass energy, you have to accommodate both those things. And the extra ingredient, of course, is the expanding universe, because there was an initial impulse of energy that led to the expansion in the first place. So if you want to do conservation of energy, you'd have to include the impulse or the initial kick that led to the Big Bang itself.
The next question is from Mr. P, who's on with us live. Could you please explain if there are any correlations between the WOW signal point of origin candidates, such as, okay, let me sort of rephrase this a little bit. Could you please explain if there are any correlations between the WOW signal point of origin candidates and any current breakthrough listen experiment data?
So the question relates to two different things that are part of the SETI project, the Search for Extraterrestrial Intelligence. The WOW signal is a sort of famous one-time signal spotted in the mid-70s, I'm not sure, 76 or 77, at a radio telescope run by the Ohio State Observatory. And there was a big spike seen on a strip chart, and the word written next to it was WOW with an exclamation, or maybe 3 exclamation marks, and it's become part of the lore of SETI that this could have been an alien signal, but since it didn't repeat, it's not considered evidence of extraterrestrial intelligence. So it's just a one-off, and it was never identified what the source of that was. The Breakthrough Project, a Yuri Milner funded project to do SETI, is targeting a wide spectrum of sources. So basically targeted searches were the old way of doing SETI, and the modern way of SETI is to look at a large number of sources to cover the waterfront by observing millions or hundreds of millions of stars at once, and that's what the Milner project is trying to do. That may include the source of the WOW signal, but we don't know where that was, and it never repeated. So I think the WOW signal has not been considered true evidence of extraterrestrial intelligence.
The next question is from a live participant. Does dark matter play a role in the cohesion of the galaxy cluster or in the merging of galaxies with each other, or is it limited to the attraction between them?
It definitely plays a role in the dynamics of galaxies in all aspects, not just the attraction between them and the way they move relative to each other, but also the way they behave when the galaxies merge or collide or clusters form. So visualize every galaxy in the universe as being embedded in a dark matter halo that outweighs the normal stuff by a factor of 5 or 6 and is also physically larger than the visible stuff. So it's an extended halo. As galaxies interact and merge and collide, the dark matter halos also interact and merge and take new shapes. They're operating entirely by gravity, of course. Gravity is a long-range force, so these halos can change their shape a lot and evolve as galaxy clusters evolve. Because there's universal attraction, the dark matter density in the center of a galaxy or cluster will gradually increase over cosmic time, and we see some evidence for this.
The next question is from Nader, who asks, Earth is in the habitable zone of the solar system. Is the sun in the habitable zone of the galaxy? Is there such a thing as a habitable zone in a galaxy?
There is a concept of a galactic habitable zone. It's been put out by researchers starting 20 or 30 years ago, actually. So the idea there for galactic habitable zone is that there is a sort of sweet spot or a range of distances in the disk of the Milky Way where life is more likely to occur. What happens as you go very far out in the disk is that the abundance of metals or heavy elements declines. That's just a standard fact of stellar evolution, and the fact that the star formation rate is lower in the outer part of the disk. So the heavy elements are lower, there's less carbon, nitrogen, and oxygen, and it's quite likely that the incidence of planets and biology is lower in the outer part of the galaxy. If you go to the very inner parts of the galaxy, especially anywhere near the nucleus, the stellar densities get very high. hundreds, thousands of times what they are in the solar neighborhood. And at that point, stellar encounters could disrupt planets. The supernova rate, or the rate of stars blowing up in a way that could destroy life on a planet, that goes up. And so the inner part of a galaxy is a potentially very inhospitable environment for biology or long-lived stable planetary environments. And so that's the basis for thinking that there's a ring in our galaxy and any spiral galaxy where you're most likely to find life. It's important to point out that this is just a conceptual argument, and nobody's found any direct evidence that it plays out in the real universe. We just don't have enough measurements to say that.
The next question is from an email from Norm, who asks, Professor Impey, in the grand scheme of things, what is the likelihood of black holes absorbing ever-increasing amounts of light and matter so that they become the dominant entities in the universe?
I think the odds of black holes becoming dominant in the universe are extremely low. Let's put them at essentially zero. Numerically and in terms of their mass, black holes represent, I think, 0.001% of the mass content of the universe. That's a really small fraction. You could use the Milky Way as an example of that. We have a 4 million solar mass black hole, and we have a galaxy with 100 billion stars and a total mass that's hundreds of billions of times the mass of the sun. So obviously the black hole is tens of thousands of times less massive than the entire galaxy. And that plays out in all the galaxies in the universe. Black holes as a form of dead stars are also a very small fraction of all stars, because most stars are red dwarfs, low mass. So generally, black holes are a small mass component of the universe, small fraction, and because their reach is limited, they cannot pull in material from very far away, because at some distance from the black hole, their gravity becomes the same as a Newtonian prediction, and they're just in a stable situation with other things orbiting and not necessarily falling in. Their ability to accrete material is fairly limited, and it's limited to the immediate environment, so they are not going to increase. Their currently very small fraction of the universe is not going to grow substantially over time.
The next question is from another live viewer. Arif asks, Sir, why is the scientific research on consciousness regarding astrobiology important? What are the unknowns so far in this area?
Well, there's huge unknowns. This is where astrobiology becomes completely speculative. So in the parsing of the terms of the Drake equation, which is the sort of organizing framework for astrobiology, the parts of the Drake equation that deal with the incidence of planets and the number of planets per system and the likelihood that they're habitable, those numbers are coming into focus through direct measurement. But the part of the Drake equation that deals with not just the existence of life, but the likelihood that life becomes intelligent or technological, both of which imply sentience, that's completely unknown because we have no other examples to study. So it is obviously a very important question how life, how biology, which starts as microbial biology, eventually develops consciousness or intelligence. We don't know how that works in general. We just know a little bit about how it happened on the Earth, and it took a long time. It took billions of years for life to evolve from single-celled organisms to multi-celled organisms to eventually plants and animals, and eventually some fraction of those animals grew brains big enough to have consciousness.
The next question is from our live viewer, Ellensburg, Washington. Good day, Professor. What is at the center of every galaxy? It is supposed to be dark if there's a massive black hole, but obviously this isn't the case.
Every galaxy, we think, does have a black hole. We've not found a counterexample to that, certainly not among massive galaxies. There are some questions about whether all dwarf galaxies have black holes, and it is possible that in some circumstances the black holes could get ejected from the centers of their galaxies. But basically all galaxies have black holes. Those black holes are unlikely to be completely dark because they're in a very dense environment. The center of a galaxy is a pileup of stars and gas released by those stars or falling in from outer regions. And so there's a lot of material to fall into a black hole in the center of any galaxy, and the acceleration of that material, its formation into an accretion disk and its acceleration potentially in jets along the spin axis of the black hole, those tend to make the inner regions very bright. So those black hole environments will glow brightly. So we don't really expect the centers of galaxies to be dark. It should be noted, though, that the Milky Way is an example of a modest-sized black hole that is fairly quiescent, that is not in a very currently active state, and so the Milky Way black hole is relatively dark.
The next question is from Alexander, who's on with us live. Hello, Professor. What are your thoughts about double Jupiters discovered in the Orion Nebula? Can such objects exist outside of a nebula that's dense with dust and gas?
In a nebula like the Orion Nebula, that's a very dense star-forming region. So the density of newly formed stars is extremely high. It's thousands of times the density of stars in the neighborhood of the Sun, for example. Orion is about 1,500 light years away. And so in those highly, concentrated stellar environments, it's possible to have, bizarre effects like double Jupiters or, planets orbiting binary stars or triple stars. All of these things are entirely possible. And so a dense stellar environment is going to lead to some exotic exoplanet situations.
The next question is from one of our live participants who would like to know, could time itself be an unknown particle like the Higgs boson?
That's an interesting speculation, and physics accommodates that because there are ideas of time where time has a particulate construct. There's no obvious example of any indication where time is a particle in the everyday world. Time appears to be a constant, a sort of construct of nature that evolves in a forward direction, but it's not necessarily carried by a particle. There has been speculation from quantum theory that time in the ultimate sense could be quantized, and so could have a quantum particulate nature on super small scales, super small time scales, just as physical matter is quantized on super small scales. So that's an idea that's there in physics, but at the moment there's no indication. It's never been tested, and there's no indication that time is quantized.
The next question is from Yashovardhan Patil, who would like to know, I think the framing of the question we can adjust a little bit, but is it possible that we don't exist yet for some theoretical aliens living in the unobservable universe, so beyond the observable universe?
Sure, because if any civilization on a distant galaxy is 4.5 billion light years away or more, then that's how long it would take light to reach us. And so at the current moment, synchronously, they would only realize we existed after 4.5 billion years. So they're sitting there right now with the Earth barely forming and no life on Earth, and they have to wait for that information to reach them over 4.5 billion years. So as soon as the time delays are that long, you have a very interesting situation. Muted.
Sorry about that. The next comment is from Ryan, who just wanted to say thank you for doing a session with the Seven Ponds Astronomy Club earlier this year, and they still fondly remember it. The question that we have next is from Maxwell Bennett. Has the recent findings of the James Webb Telescope changed astronomers' view on the Big Bang? If so, in what way? It can be difficult to keep up with.
The James Webb has not fundamentally altered the idea of the Big Bang. It has created an issue that is one that is concerning some astrophysicists about how mature, well-developed massive galaxies and their massive black holes could evolve so quickly in the universe in, say, less than 500 million years after the Big Bang. So that's one of the things James Webb has shown through its study of distant galaxies. But this is not a Big Bang breaker, if you like, as an observation. It's just a significant challenge to our theory of galaxy formation. It would take a lot more than, a handful of mature, massive galaxies in the early universe to overthrow the Big Bang theory, because it's based on a very strong tripod of evidence.
Excellent. The next question is from Karen Martin. Good afternoon from the UK. Karen would like to know about black holes. If you were approaching the black hole, assuming that you were still conscious in an unlikely scenario, as you get nearer, time appears to slow down. Would you reach a point just before crossing the event horizon where time had slowed so much that it appeared to stand still? And how would this be seen by a distant observer?
So the relativity of the situation is interesting. It is the distant observer that would see your time slowing down and would see you, the infalling person, and their spaceship frozen to eternity, frozen at the edge of the event horizon, just at the point of the event horizon as the time slowed down infinitely. But in your perspective, as the person falling in, you would be following what astronomers would call ballistic trajectory, just caused by the gravity, moving fast, possibly close to the speed of light, and you would pass through the event horizon at that speed, and your clock, as seen within your situation, would appear unaltered. So the relativity is such that that slowing down of time asymptotically only occurs for a distant observer watching the person falling in.
Excellent. The next question is from a live participant. What are the chances that life developed when, after the Big Bang, the average temperature of the universe was when liquid water could exist, and what are the chances that life exists to this day?
So it's an interesting question. How quickly could life have developed in the universe? That question is alluding to the fact that in the hot Big Bang, there's a period of time when the universe is too hot for stable matter to exist, for neutral atoms to exist, and that takes you to about 300,000 years after the Big Bang. And then there's a later time, but it's only some few million years, where the temperature of the entire universe goes from the boiling point of water to the freezing point of water. And at that point, in principle and in theory, you could have liquid water in the universe. The trouble is there's no way for liquid water to have been made. So even though the entire universe at one point did have the temperature of liquid water, it's not a universe with water in it, because this is before the formation of any stars, and so there's no oxygen been made that can then combine with the hydrogen to make water.
So we have a different person, but a follow-up question on the rogue planets. So based on what you were saying earlier, rogue planets could basically exist infinitely as rocky objects, longer than any star in the universe. Is that accurate?
Yes, if there's no force degrading them or diminishing them, their rocky material will persist. It's not going to decay. There will be some radioactive decay within the rock, but the rocky material itself is extremely stable. Infinite is always a tricky term, because if you really take infinite, then some theories of physics suggest that protons are unstable, and if normal matter is unstable, then everything will disintegrate, including planets, but that's not confirmed by observation.
The next question is from Akshata. What do you think, or when do you think dark matter began? So that's the first question, and then there's a second one after that.
So dark matter was built in to the universe at the beginning. So as the universe came into existence in the Big Bang and expanded from an extremely hot, dense state, radiation and particles and antiparticles were in equilibrium. So radiation was creating particles and antiparticles, and then they would annihilate and create radiation and so on. A slight asymmetry between the matter and antimatter led to the excess of the small amount of matter and a much larger factor, hundreds of millions times larger number of photons. But dark matter was built into that. So whatever the dark matter particle is, and I'll presume for the moment that dark matter is a new type of fundamental particle, that particle was created very early in the universe, in really less than the first few minutes, probably in the first microsecond after the Big Bang.
The next question, so the second question from this same group of questions, is it possible that there is a dark matter star somewhere in the universe?
So having large concentrations of dark matter would be very unusual. So there has been speculation about, dark matter stars or stars with large amounts of dark matter relative to normal matter. But that's not a likely scenario because dark matter only obeys the force of gravity, and so the clustering strength of dark matter is very slow over cosmic time. Whereas when stars collapse, they collapse from the gas, and the gas in gravitational freefall can be shocked and heated, and of course eventually reaches a temperature where fusion can occur, and that's how you get a star. So normal matter is subject to behaviors and physics that dark matter is not subject to, since dark matter only responds to gravity.
The next question is from Kendra Smith. Can you explain why the gravity of other stars has no effect on the Earth? It seems like it should, even if only just slightly.
It does have an effect on the Earth or on the solar system. So the gravity of the nearest stars, remember the nearest stars are a couple of light years away, and there's probably 50 or 60 stars within 10 or 15 light years of the Earth. Those stars definitely influence the planets and the sun, but the solar system is a bound entity. So the way physicists talk about this is a sphere of gravitational influence. So all the planets are within the sun's sphere of gravitational influence. Now the sun can be affected by another star, but the behavior of the planets is going to be dominated by the sun because they're within the sun's sphere of gravitational influence, not within the sphere of gravitational influence of a distant or neighboring star.
The next question is from Yashovardhan, who asks, if we were able to study dark matter more, would we find a dark elemental spectrum as well?
Well, it's unlikely that we'd see a spectrum of dark matter because to see a spectrum, you'd have to have an interaction with electromagnetic radiation, some form of interaction, whether it's absorption or emission or scattering or polarization even. Since dark matter apparently, almost by a premise, doesn't interact with electromagnetic radiation, it is therefore not logically going to create any spectral signature or footprint. So that, unfortunately, is not a way we can detect dark matter or diagnose it.
Excellent. The next question is from one of our live participants. Let's see. Lawrence K would like to know, how does gravitational time dilation compare to relativistic or Lorentzian time dilation?
Gravitational time dilation is a very small effect because essentially gravity is an incredibly weak force. So gravitational time dilation has been measured by atomic clocks. These experiments were first done in the 1960s, maybe even in the 50s, from atomic clocks that were on the Earth's surface, an identical clock flown in a high altitude plane, resulting in the fact that the clock on the ground in slightly stronger gravity kept slightly slower time. This is a very small effect. It was 1 part in 1,000 trillion, I think, the initial experiment. And so that's a much smaller effect than Lorentzian relativity dilation.
The next question is from one of our live participants. Jose asks, can you explain the relationship between space velocity and space-time?
Space-time is the construct of the universe. It's essentially the four-dimensional manifold, to use a geometric term, but 3 dimensions of space and 1 of time that are conjoined and denoted as conjoined by the equations. And the universe is an expanding situation of space-time. Space velocity is a different thing. It's an attribute that we give in physics or astronomy to any physical object moving through space-time. So it could be a star, could be a galaxy, could be a rocket, could be a particle. And it will have a space velocity, and that's a three-dimensional velocity. So it's a velocity with a vector attached to say what the direction of the motion is.
The next question is from DS, who's on with us live. Hi, Professor. Does astronomy's current inability to explain what dark matter is indicate that astronomy itself is an unreliable method of learning about the universe? Apparently they were told this recently, and they would like your view on it.
I don't think the ignorance about dark matter is a representation of astronomy being unreliable as a subject or as a method of learning. It just means that astronomy is incomplete and has significant challenges and issues still to resolve. The fact that we don't know what dark matter is does not take away our ability to explain how stars work, how they make heavy elements, how galaxies are put together, how the universe is expanded from a small situation to a large, low-density, cold situation, and will expand in the future. So not knowing what dark matter is doesn't take away any of the explanations we've made successfully. But it is a big caveat on our understanding of the universe, because dark matter, is dominant in the material universe, and so it dictates how the expanding universe behaves as well as how galaxies behave. So to not know what it is physically is a huge hole in modern astrophysics.
The next question is from David Wismer. The Higgs field seems to be homogeneous. Why doesn't it clump like dark matter or dilute with the expanding universe?
I think in the physics of it, the Higgs field doesn't clump like dark matter because it's not responding to gravity. So the Higgs field has no attractive force component that might lead it to clump in any way. And in fact, it's a fundamentally different type of entity. So it doesn't behave the way photons would behave, or the way gravity would behave, or the way normal matter would behave. It's a field that permeates space and has something analogous to a viscosity, which explains when particles move through that space, how we attribute mass to them.
Excellent. And then kind of a follow-up to that, if it doesn't dilute, where does the energy to make this field come from?
Well, that's a good question. The energy to make the Higgs field was present at the creation. It's built into the universe. It's part of physics. It's essentially a fundamental field, just like the electromagnetic field is a fundamental field, and that permeates space too. So it was built into the creation, and we would have to know a lot more about the early universe to diagnose when and how the Higgs field came into being.
The next question is from Saeed, who asks, so we already talked about this a little bit earlier about how that consistency of physical laws is sort of a premise for modern astronomy. But Saeed would like to know, is it possible that the laws of physics continuously change slightly as the size and location of objects changes, and we see a difference in results and predictions only at extreme positions?
The constancy of the laws of physics is something people worry about and do try and investigate. It is possible that laws of physics change somehow in situations either in the extremes, where there's a lot of action and activity and density and motion, or in the other extreme, where it's intergalactic space, nothing particularly happening except expanding space-time. So the best we can do is to look at fundamental constants like the fine structure constant and see if those vary across the universe or across galaxies, or to look at fundamental chemistry and see if the chemical elements, the ingredients of our universe, change. And we've never found any examples of those changes. So we've never seen an example of the laws of physics changing where, say, the gravity force is evolving in a different way from the electromagnetic force. If that were the case, it would have some signature effects on distant galaxies and their spectra, and we haven't seen that.
Jake Johnson has a question. who's on with us live. Hello, I'm in my mid-40s and would love to get involved in astronomy professionally. Can you offer any advice on what paths I might take getting involved this late in life?
So for a late arrival into astronomy and an interest in that profession, it's tricky. The requirement to get a job is still a degree, one or more degrees, but you can get an astronomy job with a bachelor's degree. You don't have to get a PhD. A PhD sort of sets you up, tees you up for research, and maybe in midlife you don't necessarily want to do research. So qualifying to get an astronomy job does require that kind of training, so at the minimum a bachelor degree. And then as for where you might work in middle age, just starting in a field, there's always some ageism in science and in the employment sectors. But there are also some jobs where skill is appreciated regardless of the age or other origin story of the participant. And so astronomy on the technical side, running observatories, building instruments, working in national labs, that's a more likely place to get situated if you start late in life than academia, where there's pretty much a standard path in academia of undergraduate, grad school, postdoc, faculty. And if you're an outlier in terms of your age, then you're sort of disadvantaged in that academic hiring landscape.
The other thing I just want to add is that NASA always kind of invites people from a variety of professions to join in their endeavors. So they need people who work in finance, they need writers, they need people from all sorts of different backgrounds, education. So depending on what your background is, that might be a way into participating in the field of astronomy, even if you're not directly working on the astronomical research. The next question is from Matthew Avery. Do certain rules of thermodynamics and the Doppler effect still take place in space? But they mean specifically, is there any sound, and does the Doppler effect affect sound in space?
The Doppler effect is based on sound. It's the fact that when a source of waves is in motion, then if it's moving towards in the direction of motion, those wave fronts will be compressed, and that leads to a higher frequency or pitch. And if it's going in the other direction, it'll stretch out the sound waves, and that leads to a lower frequency or pitch. So you need a medium to propagate sound waves. You can't have sound waves in an absolute vacuum. It is true that there are some very diffuse mediums out in the universe, like in the intergalactic medium or the interstellar medium, and then technically you can have sound waves through those media. However, they would have extraordinarily low wavelengths, long wavelengths, and very, very, very low frequencies compared to the sound waves we're familiar with.
Athulya would like to know, inside a white hole, does time run backwards like anti-time?
That's a matter of pure speculation. So Kip Thorne and other gravitational theorists have written about white holes or the possibility of white holes. And yes, there are some formulations of the white hole scenario where the time would run backwards. But there's no evidence that white holes exist in the universe, so we're definitely several stages of remove from understanding how the physics of a white hole works.
The next question is from Ryan, who's on with us live. Can you please explain what a quark star is?
So quark star is an extremely dense star, dense stellar state, where in the neutral material that forms this highly concentrated state. Remember, have some stars, like neutron stars, that are as dense as atomic nuclei. When you have something that's as dense as an atomic nucleus, you can create a situation where the quark confinement, which normally keeps quarks tightly bound in pairs and triplets, the triplets, for example, are neutrons and protons, and the doublets are pions and kaons and other particles, where that bound loosens and the quarks start to move around within the highly dense medium. And that's really what a quark star means. It means the quarks are partially liberated to express their behavior within the context of a superdense state. That's a matter of complete speculation, so it's very hard actually to prove that a quark state of matter exists within a star, and nobody's done it yet.
The next question is from Manuel, who would like to know, can we say that gravity is a force? And what's the difference between a force and like a field or some other quantity or thing in physics or astronomy?
We can certainly say gravity is a force. That's a kind of a classical physics way of describing gravity, because in general relativity, gravity is not described as a force. Gravity is described as the reaction of particles and photons to curved space-time, where mass and energy curve space and time, and then particles and matter respond to that curved space-time. So that's a very different, geometric formulation of gravity. So we can have these different formulations of gravity, and they are internally consistent, but in this case the general relativity formulation is the superior one.
Oh, sorry about that again. The next question is, what's your opinion on the baby galaxies paradox? Are you familiar with this, and can you talk a little bit about what your opinions are?
Yeah, baby galaxies is, again, galaxies that may be small, but they're mostly very early in the universe, and so the question is, can you form galaxies that are mature of any mass early in the universe, in the first half billion or a few 100 million years? It's not fully a paradox yet. A paradox is a complete logical inconsistency, so I wouldn't say any type of galaxy in the universe that we've studied forms a logical inconsistency, because it's actually very hard to measure the mass or ages of very distant galaxies. So we simply don't know their characters well enough to decide their true physical nature, and therefore I don't think they exert a big problem in cosmology, but they're definitely intriguing and worth following up.
The next question is from Matthew Avery. Do you think it was really a meteor that killed the dinosaurs, or did something else, such as a flood or disease or something else, have a role in it as well?
The current thinking is from interdisciplinary work that involves paleontologists and geologists, and climate scientists, is that it wasn't a single event that killed the dinosaurs. There's very strong evidence now of a 1-2 punch, where actually the impact, the KT boundary impact that's seen in the fossil record and in the geological record, was the second sort of death blow to large creatures on the Earth. And the first part of the blow was a large geological event that created a huge amount of volcanic activity, and also raised the carbon dioxide content of the Earth and put a lot of smoke in the atmosphere. And there's research just even in the last few weeks that has tried to measure what the impact of that volcanism was on life, just in terms of its change in the atmospheric composition and temperature and increase of particulates. And it's likely that that was a very strong effect and had literally a smothering effect on life. So it's very likely that the geological impact or the geological event was the stronger and determining factor in the extinction as opposed to the asteroid strike.
The next question is from an email. Pramod would like to know, can you please explain how a star shade will be used to photograph exoplanets? Can you talk a little bit about how the shape of the petals will be used to block the light from the distant star?
So a star shade is an object that's typically in the formulations that's going to be used. It's a free-floating device, a screen with a very complex shape that sits in front of a telescope and almost perfectly blocks out the light from a central star to leave visible the much weaker, billion times weaker reflected light of a planet. And the star shades in most designs does have a sort of flower petal like shape, and that's because it's associated with the diffraction pattern of light, and the telescope has its own optics. Of course, it has a rib structure, it has internal elements that support the mirror, and they affect the way light behaves in making an image. And so a star shade is designed to sort of compensate that and create the perfect diffraction limited counterpart to the central image, and therefore subtract it out by physically blocking it. So star shade design is a fairly mature process. People have been doing the design for decades, but the first deployment of a star shade for a telescope to look for life on planets has not happened yet.
And then, let's see. The next question is from Guy Gagnon, who asks, is artificial intelligence currently utilized in astronomy? And can you talk about some examples of how it's used, if so?
Yes, AI is used heavily in astronomy now. Many scientific fields have utilized machine learning and AI methods. In astronomy, one of the main goals often is to deal with weak signals in the presence of a lot of noise, or look for needles in haystacks, if you like. And AI is very good at that. So if you want to find rare types of objects in a sea of other objects that are more routine or mundane or normal looking, then AI can be trained to look for anomalies. So that's a very powerful use of AI. And that's good for whether you're looking at exoplanet transits and therefore new types of exoplanets, or you're looking for strange galaxies in a visual field of a deep image of the universe, or you're looking at a time sequence of transients, and you're trying to pick out a new signature, not for an exoplanet, but just maybe for a variable star or something like that. So it's a very powerful technique that is used essentially across astrophysics now.
Excellent. The next question is from one of our live participants. Can you talk about whether the electromagnetic spectrum has been stable through time?
Yes, there's no indication that the electromagnetic spectrum is variable over cosmic time. We can't access all aspects of fundamental physics in astronomical measurements. The quantity that has been measured fairly well over cosmic time is the fine structure constant. And the fine structure constant is a numerically about 1 divided by 137. That's its numerical value. And it's a combination of fundamental physics constants, including the speed of light, which is implicated in electromagnetic radiation. And that fine structure constant, there's been occasional indications that it might vary over time, but the limits on it are very strong, and so that's the best evidence we have. A little indirect, that electromagnetic radiation has not changed over cosmic time.
Excellent. Thank you very much. So it is now 11 o'clock. We're going to take one final question, and then we will wrap up. There is a live participant who's interested in the length of a day and an hour and a second. So I will say that for the exact quantities, you can go look those up online, and you will be able to find those to more accuracy than we can give you. But Chris, can you talk a little bit about the background of where those quantities come from?
Yes, the short units of time, the long units of time like year and month are obviously associated with the Earth's orbit around the Sun and the Moon's orbit of the Earth. The day is associated with the Earth's spin between, pointing the Sun being directly overhead from one day to the next. And the subdivisions of time sort of follow from that. The second has now been defined, since it's a metric unit, it's one of the fundamental metric units, has been defined in terms of atomic vibrations. So it's a very large number of vibrations of a fundamental transition in an atom, and that's just the standard metric definition of it. And that should be universal, because those atoms and their oscillation strengths exist throughout the universe. The civil time, that is the timekeeping, not of physics but of human affairs, of course has to use times that are variable because the Earth's orbital situation changes. And so the civil time second occasionally has to be recalibrated or reset. And so the business of keeping time on the Earth is a fairly complex matter, of course, but it's mostly due to the irregularities in the Earth's orbit and its spin, and the uneven geometry of the Earth itself, which is not a perfect sphere. So that's the short version of what is a very large subject. Books have been written about this. So appreciate the questions, covering a lot of ground as usual. And I don't remember, I think we do have one more on the books up ahead, but we'll keep up our cadence of every other week, roughly, for the live session. So appreciate Matthew for facilitating, and we'll be with you in, I think, a couple of weeks. Maybe Matthew can see when the next one is, but I don't know.
I can indeed. The next one is in 2 weeks from today. It's Thursday, November 2nd, same time, same bat channel. So exactly 2 weeks. So we will see you all then.
Okay, thank you.
All right, take care, everyone.